Welcome everyone to this third educational session on artificial intelligence and its application in hematology, organized by the ERN-EuroBloodNet and the Synthema project. My name is Sarah Reidel. I am the biostatistician of the Enroll Registry, the official registry of the ERN-EuroBloodNet, and data-driven lead in Mark's Manu group, that is one of the use cases in the Synthema project. And she's also part of the ERN coordination. Please remember that we have one more session next Friday, and that all sessions are recorded and uploaded to the ERN-EuroBloodNet YouTube channel and website if you want to share this information. Then some housekeeping notes that you should keep in mind. Your microphone will remain muted during all the presentation. Of course, this webinar is being recorded, and you can submit your questions via the questions and answer chat box, but we will be answering after the blog session, each blog session. Then you can turn on your Zoom AI translated caption. To do this, please go to the button CC, enable the translation, select the speaking language, in our case the English, and then your caption language. Okay, so you may have seen that we are a lot of speakers. So this session is on data quality, standardization, synthetic data generation, anonymization, and interoperability, and has been divided in 3 blocks. The first one, data quality, data standardization, and interoperability, will be presented by myself and Giulio Spinozzi. The second one, synthetic data generation, anonymization methodologies, will be presented by Sofia Tequerido, Imanol Isasa. And the third one, building trust in synthetic health data, methodological and acceptance challenges across 7 European projects, will be presented by Rafael Redondo Tejedor, Inés Sousa, Max Salvi, and Jan Ramon. So with this, I will present. I am the first speaker, so I have to turn to the other presentation. Give me 1 minute. Okay. So the first block is on data quality, standardization. Sorry, I cannot see. Okay, now. The first block is in data quality, standardization, and interoperability. So the first question that I made always is why we are talking about data quality in an AI webinar. And I think it's because of this. It's becoming increasingly common to find that algorithms don't always get it right. We are seeing models that misclassify patients based on ethnicity, systems that underestimate health needs because they were trained on biased data, and hiring tools that replicate the discrimination that we are trying to eliminate. So we need to ask ourselves, is this a problem on the model or is it a problem on the data? And I think that we all agree that the model learned correctly from the data, but the problem was indeed in the data. So what is the current context for the data in rare diseases? You know from last sessions that nowadays it has been identified more than 7,000 rare diseases. This means that more than 30 million of people in Europe is living with a rare disease. That the knowledge is dispersed and also the experience, that there is a lot of lack of evidence to develop treatments and clinical practice guidelines, that there is insufficient passive translational and clinical research, that as we are in the context of rare diseases, there is a huge lack of a sufficient number of patients or patient groups. And because of all this, in rare diseases, we rely a lot on real-world data and the generation of real-world evidence. But you may know that the real-world data has its own challenges. Normally, it's scarce, it's fragmented, and is unstructured. And all has made that, for example, most of our patients are underdiagnosis or misdiagnosis, or even they have delayed diagnosis. We have identified that for a patient living with a rare disease, it took, for example, 5 to 7 years to get a diagnosis. So you can imagine what is living 7 years without not knowing what is happening with you, for example. So, as the utility and interest in real-world data increases, some guidelines and legislations are in process to deal with all the challenges that I described. In particular, with the low internal validity that real-world data has. One of the first official guidelines that has been released is the one released by the European Medicine Agency on data quality framework for real-world generation. In this guideline, 5 dimensions are described to assess the quality of the data, and 4 levels are described to identify the maturity level of the real-world data source, let's say. One, analyze the quality of the data, the other, analyze the quality of the process that are in place to get this real-world data, and at the end, produce real-world evidence. So, for data quality, 5 dimensions right now are being described. Extensiveness, this means if your data is sufficient. Coherence, it means that if your data is analyzable. Then timelines, that this means that if the data is right at the right time. For example, we have a lot of chronic organ damage. For chronic organ damage, you need years on the natural history of the patient to be developed. So if you have, for example, data only on 1 year of the patient, probably you won't have evidence on chronic organ damage on this patient. Then the relevance. Are the data of the right kind? I am collecting the data that I need to answer my question. And then finally, but not less important, the reliability of your data. Is the data faithfully representing what it's meant to be? On the other hand, all this data quality relies on the process that you have in place in the system that you are using to collect all this real world data. So the first level, that is always the starting point, is to have documents. Organization needs essential documentation such as data dictionaries, operational processes, variable definition, data capture flows, and everything. Then you need to standardize this documentation. And this standardization enables reproducibility and comparability across centers or countries. Because you know that for rare diseases, it's not enough with the center, and it's not enough with the country. So you need to standardize the process that everybody is using to collect this data in order to assure the reproducibility of what you are getting from that data. Then the implementations. Once the processes are standardized, they can be systematized. And finally, the automation. This means that all what you have done is now understandable by machine. Then another important thing regarding the data quality and utility level is the European Health Data Space. Nathan presented last session the European Health Data Space as a whole, but particularly one article, the Article 78, speaks about the data quality and utility level. And we know now that the European Health Data Space will ask for all the data coming from electronic health data and processes with the support of national or union public funding. They need to have a data quality and utility level covering all the elements that are expressed in this in this Article 78. We have compared the Article 78 with the EMA guidelines, and they are very aligned. They are not asking for nothing new. So we can be sure that everybody is going in the same path, in the same way. So what we have been doing in the ERN, considering all this context. First of all, we have the enroll registry that collects and standardizes data on more than 450 rare hematological diseases. To do this, the first thing was to divide all these diseases in 2 hubs, onco and non-onco, and then to organize these disease groups in 6 sub-networks. For all these 400, more than 400 diseases, we are collecting 16 parameters that are transversal to all rare diseases and allows to facilitate epidemiological surveillance, enhance health planning, enable the identification of patient cohorts, and promotes research and innovative therapy. Then, under the umbrella of the enrolled registry that is for all rare and hematological diseases, we have the RADIP registry. The RADIP registry focuses in the rare anemia diseases, one of these sub-networks that we have described in the enrolled registry, collects much more information, and with this information we can answer epidemiological questions that as we do with enroll, but also we can study disease progression, prognosis, and response to treatment. Everything with the final objective to getting a better healthcare for rare anemia diseases patients. RADIP has been officially endorsed by the European Hematological Association in 2024. And based on all what we have learned about the EMA guidelines and the European Health Data Space article on data quality, we have created a whole ecosystem that connects enroll and RADIP to all the European strategies for rare diseases, including not only collecting the 16 parameters that for them are essential for health planning, but also to try all these tools and software and systems that they have been developing for making the data on rare diseases interoperable, reusable, findable, and accessible. We have developed, for example, solutions for all our data providers to enter data and standardize the data that they have in the different countries and in the different hospitals. Right now, in RADIP you can enter the data manually, and we took care about the backup policies, the data management, the user management, and everything. Then we have also created mirror systems. This means that they have all the same facilities that the RADIP center, but the system is hosted in their servers. And then we have also worked in the interoperability between local solutions and RADIP to also be able to transfer the data. Then, for those countries or those data providers that are using our RADIP Central or our mirror system, this data that we can assure the quality of the data because they are collected 100% under the RADIP registry ecosystem, we use this data in a sister platform of RADIP called Radiant. This platform was created with the purpose of clinical outcome research platform in rare anemia diseases. It's the objectives of this platform is not epidemiological, it's more on AI, post-authorization safety studies, post-authorization efficacy studies, and the reuse and linkage of this clinical data that is collected in RADIP with other type of data like genomics, metabolomics, radiomics, etc. Also, which are the tools that we have implemented to be able to analyze if we are covering all the dimensions on data quality that the EMA, for example, is asking. We have now a published dashboard where you can see in real time the amount of patients that we have in our registry. You can see stratified by age of the patient, you can see stratified by diagnosis, and you can see the total patients that we have in each country to see the representativeness for how much are we covering in each country, let's say. Then we have developed some private dashboards. These dashboards are used by our data monitor and our data providers to see some descriptive tables on the data with important information they need, for example, to be able to see if their hospital are feasible for clinical trial, what type of data they have, is in pediatric, is in adult, the diagnosis, and this type of thing. To identify cohorts, for example, cohorts of patients for clinical trials. With these tables, they can do this somehow easily. Then they have completeness report and coverage report to see the quality of the data also, how much we are covering on the information that we are expecting. Then we have developed a pseudonym module. This module right now is capable to pseudonymize patients, and in the near future we'll be able to lead with duplications between different registries. This means that not only if we detect duplications, not only inside the same hospital or in the same registry, but will be able to detect duplication between registries in different diseases, for example. Then another thing that we need to somehow develop is our study population. So we have identified five study populations. The first one, of course, is the target and the one that we want to achieve. Then we have the accessible population. This means that somehow we know the amount of patients that we have in Europe. Then we have the intended population, that is the population that we know that we can reach according to our collaboration agreement and the resources our data provider have. And then we have the actual or registry population, that is mean the patient that we actually have in our registry. For the registry population, right now we are collecting more than 200 parameters. And besides of defining this study population, of course, we have a lot of documentation, including the data dictionary. The metadata of these registries is available in different catalogs, and also the data has been mapped to the OMOP common data model. Then, for our specific use case in Synthema, what we have learned once we have put in place all these tools to know the quality of our data. For example, now we are very aware of the clinical outcome heterogeneity that this disease has. You can see the country distribution of genotype of this patient, the heterogeneity of the heterogeneity that the distribution of the genotype has on this patient. You know that the genotype is one of the most disease modifiers of this disease. Then you can observe also the heterogeneity on the severity of the patients in the different countries based, for example, in the percentage of patients suffering 2 or more VOC per year, the patients that are being treated, the hydroxyurea treatment, or patients that are in regular transfusion treatment. Then, as we have the accessible population and we have now the registry population, we could do a bias assessment. And doing this bias assessment, we evaluate the likelihood of the patient to be enrolled in our registry based on its individual characteristics. And we have identified that in our registry, pediatric patients or patients with less frequent genotype, and even something that this was in fact a surprise for us, patients that are less severe are more likely to be involved in our registry than in the survey. That was our reference, our accessible population. So finally, to finalize this presentation, I want to introduce a topic that will be further developed by my co-presenter Julio, that are the common data models. This means that we have the data, but we need to be sure that this data is understandable by machines and by any system. So as today, we have worked with 2 common data models in our registry, with OMOP and with FAIR. OMOP, you know that is more, the main objective of OMOP is more observational research and population level analysis, and for FAIR is more on real-time clinical data exchange. OMOP is the most widely used common data model in hospitals and research settings globally. It's completely interoperable with FAIR and also with CDC, that is the model that pharma companies use to standardize the data in their data dictionary. FAIR is more to move the data. So it's important to understand that these common data models don't compete between them, but close all the life cycle of the data, let's say. CDC structures data collected in trials, for example, or MOP standardized data coming from real world data, and FAIR moves the data between systems. This is how they work all together, let's say. So I don't know if Julio is here.
There it is. Oh, thank you, Sal. I try to share the screen.
Let us know, Julio, if you see your share button. Otherwise,
yes, I'll try.
Now you should be able.
It's
If
not.
not, I have your presentation if you want that I present.
No, if you can share the, you should have my presentation. Thank you very much, Sarah.
Well,
Okay, thank you. Good morning, everyone. I'm the CTO of Data Wizard, and in this section, I will try to explain how Data Wizard contributes to the standardization and preparation of healthcare data for synthetic data generation in Synthema. At Data Wizard, our role is focused on building interoperable and reusable data infrastructure. For example, the common data model is one of them. In healthcare, especially in rare disease, data is often fragmented and is difficult to share across institutions. So for these reasons, before generating synthetic data, it's essential to create a common and standardized structure. Within Synthema, this is achieved through the adoption of, as Sarah said, the OMOP common data model and the implementation of an ETL. In the task 1.3 of Synthema, we focus on designing and testing the ETL process used to transform clinical dataset into OMOP common data model. The main objective was to make data standardized, compatible, and reusable across the whole consortium. The standardization is fundamental because it creates the basis of the downstream activities such as data quality assessment, federated analysis, and synthetic data generation that are the main parts of Synthema. And the ETL pipeline was developed using OHD's ACI tools and applied to different datasets. The AML dataset from Humanitas, for example, and the single cell disease dataset from Valdebron. Although the datasets are clinical different, they were processed using the same architecture and methodology. The ETL workflow was we can move on next slide. Okay, the workflow. This is the yes, the workflow was designed modular, reusable, and reproducible. The infrastructure is based on Docker containers and PostgreSQL, allowing the entire pipeline to be executed consistently across different environment and platform. Several tools were integrated into the workflow. That is White Rabbit for source data profiling and structured analysis, RabbitInet for mapping source variables to OMOP concept. Is the previous slide, Sarah?
okay. This one?
The 18 slide. I don't. It is one. Okay.
The following is this one.
Okay. No, this is okay. Next.
Here it stops. So
No,
I don't
no,
know
no.
if I.
No, the previous. The ETL workflow. Okay, no, you can remain on that, and it's not a problem. The tools, as I was saying, is White Rabbit for source data profiling and analysis, RabbitInet for mapping the OMOP variables, the OMOP concept, Python and SQL script for transformation, validation, and export process, as you said in the figure. In addition, we develop a custom script to improve data validation and consistency check and generate standardized output, flat output in particular, tabular data for data inspection and sharing. One important aspect is the reproducibility. Any partner with the required dependencies can deploy the same pipeline and obtain the consistent result. This is very important in the federated learning infrastructure. As you said, this is the main diagram in which you can see that the extract pipeline starts with the source file that is a CSV, and that we perform the data preparation in Python and using on the tool that I said, White Rabbit and RabbitInet. Then we use the transformation step with the common data model initialization, setting the OMOP schema in the database, and loading the vocabulary from Athena, that is a online tool that is able to map each variable. Then we staging the layer with the import structured CSV data into the sharing schema, and then with the custom script, the SQL script, we tailor the ETL script to the local structure. Then and finally we have the ETL execution with the transform, clean, and load into the OMOP. The last step is just the load step in which you can use the OMOP dataset to be inserted in the Docker structure for the federated platform. Next, please, Sarah. As I said, the last step is to validate the dataset. We had a clinical validation that is performed by our clinical partners, Humanitas and Vall d'Hebron. And as I said, this is an important step because we have to validate each mapping feature. And then we have the last step, that is the OMOP data quality validation, in which it is mainly validated by a tool that is Achilles. This tool automatically checks the completeness, the data consistency, and the vocabulary mapping. Next, but I think that okay, this is all. Thank you.
So I see a question that is, what platform is used to create the Radit dashboard? They are made in two things, in Power BI and in Shiny. So I don't see any more questions. So if you want, we can jump into the second session with Sofia and Imanol.
Thank you, Sarah. I will be starting and then Imanol will follow. Let me share my screen. And please let me know if you can see it in presentation mode. Can you see it?
Yes.
Okay. So hello from my side as well. My name is Sofia Tekeridou. I'm a Senior Research Innovation Management Manager at Netcompany in the Research Innovation Development Department. And today we'll be presenting together with Imanol Isasa from Vicomtech on anonymization and synthetic data generation, both generically the approaches and what we have done within the Synthema project. I will start with anonymization for clinical data sharing, and then once, of course, we anonymize or synthesize data, how these data are discoverable, and the adoption of the health ticket AP in line with the European Health Data Space implementations. As actually I have briefly presented in the last webinar as well, when talking about privacy, and anonymization is actually targeted to enhance privacy when sharing, especially clinical, personal, and sensitive data. What is vital for clinical data sharing, for clinical research innovation, is to be able to share the data. We mentioned last time that we do have currently siloed data centers, which actually prevent this type of innovation or clinical research. What can be done actually is to enable data sharing. One way to enable data sharing is anonymization. Another way is synthetic data generation. According, of course, to the regulations, especially for clinical contexts, and as Nathan mentioned in the last webinar, GDPR, the European Health Data Space Regulation, National Data Protection Regulations, what is required, especially for sharing real-world data, is full data anonymization, so that the re-identification risk is minimized and privacy is preserved and protected. I will focus more on the European Health Data Space Regulation here. Why? Because, for example, Synthema, as well as other projects, in sharing clinical data, they actually follow the secondary use of clinical data aimed for research innovation and policy making, which is also foreseen in the European Health Data Space Regulation. This regulation builds on a GDPR, Data Governance Act, and the NIS2, and defines clear roles and responsibilities for digital health authorities and health data access bodies, which will be vital roles actually in this health data sharing ecosystem. So what does EHDS define about secondary use of data? It defines conditions under which health data can be accessed and processed for purposes beyond direct healthcare, such as research, policymaking, and innovation. It also requires member states to designate, as mentioned earlier, health data access bodies to facilitate access to such data, while at the same time ensuring security, privacy, and compliance with data protection laws. It defines further the minimum categories of health data that must be made available for secondary use, including electronic health records, genetic data, and healthcare-related administrative data. It further defines strict technical and legal safeguards that are aimed to prevent re-identification and ensure that data processing remains in a secure environment. So such types of safeguards, among others, of course, are anonymization, as Sarah mentioned, pseudonymization, etc. And we will focus in this talk about anonymization. And of course, researchers and organizations that are to be accessing this shared data, even in full anonymization, for their research, for example, they must apply for data permits, and the requests are assessed based on transparency, necessity, and public interest. So this is what the European Health Data Space Regulation defines, and in part what we have actually tried to accommodate as well in Synthema. Before, however, going on what we addressed, I will try to give a few definitions and general training on the anonymization processes. So within anonymization, we identify the direct identifiers in the variables of the dataset, which directly reveal the identity of a person in the dataset, like the name of the person or the address. And we also identify the quasi-identifiers, which cannot directly reveal the identity of a person in the dataset, but if combined, they can lead to the identification, especially if combined with other information, such quasi-identifiers, for example, are age, gender, occupation, etc. So it does not, what I want to mention with this is that it does not suffice simply to remove or suppress the direct identifiers, because still the dataset that is shared through quasi-identifiers can lead to identification of the identity of the person that is related to this data. So in anonymization, there are quite widely used state-of-the-art anonymization approaches. For example, one is aggregation that replaces the data values with a single group value after having the data split into clusters. As an example, the exact addresses are excluded from the dataset, but you can add the number of people living in that location, which can be known. Then it's the date shifting, according to which a set of dates are randomly shifted, but the sequence and the duration of a period of time is preserved. So, for example, the date of birth, which is a quasi-identifier, if this is the original date of the patient, then in the anonymized data, we can actually add a constant a constant shift of, let's say, 30 days and convert it like this. The encryption, of course, is one way of anonymization because data are encrypted and they cannot be reverted back if you don't have, of course, the encryption key. That's why the encryption key needs to remain private. If it is known, then they can be decrypted. Generalization, it reduces the resolution of the data, for example, from the exact date to the year, or from the exact age to an age group and age rates. If this is the birth data, then the anonymized data will simply have only the birth year or a range of 90 to 95. Masking, which replaces all or partial values with other characters of string data. So if you have this patient ID, for example, in the original data, then you can replace it with this, you mask it. simple techniques, of course, but combined actually lead to a high degree of anonymization. The noise addition that adds white noise into the original categorical or numerical data. For example, the age 25, we can add noise and convert it to 27. The pseudonymization that Sarah has already mentioned. Instead of John, we, for example, pseudonymize the name and say patient 1. Suppression, we remove some especially direct identifiers. So if we have the country of birth and the current city, we can remove the current city, so we generalize. It's a matter of also generalization in suppression. Then we have the temporal relativization, which express dates relatively to a reference date, like the birth date. So if the date is this one and the date of the diagnosis is that one, then the anonymized data can change this date to 0, a reference point, okay, and have that date of diagnosis accordingly changed to 2. So 2 days after date 0, okay? The tokenization that replaces the attribute with a non-reversible token that can be used for joining data without revealing the original attribute. So if the patient ID is 12345, then this is replaced with this token. So these are some of the standard anonymization techniques. Of course, in the literature, there are many more advanced anonymization techniques have been presented. In addition, in anonymization, we define metrics to measure the quality and performance of the anonymized data sets. And this is also a trade-off between the final utility retained in the anonymized data set versus the privacy achieved. Okay, so we always have to define these types of trade-offs between utility and privacy. So here in Synthema, we have used state-of-the-art privacy metrics and utility metrics like k-anonymity and L-diversity for privacy metrics, and for utility metrics, information loss, statistical similarity, and distributional consistency. And the k-anonymity ensures that each patient is indistinguishable from at least k-1 others based on the quasi-identifiers that we have identified in our anonymization strategy. And the L-diversity ensures that the sensitive values within each group are sufficiently varied. Whereas in the utility metrics, we have the information loss, which measures the numerical distortion that is introduced by anonymization. Of course, these require the initial real data to be measured. The statistical similarity for numerical variables compares the means, variances, and correlations between the same attributes in both the original and the anonymized datasets. And the distributional consistency, which is for categorical variables, measures the extent to which category frequencies are preserved after anonymization. But for some methods, it is not available, like for suppression. Now, in Synthema, we have tried to implement different methods for anonymization. First, we developed a local anonymization engine that is based on state-of-the-art anonymization algorithms, but capitalizes on defining customized anonymization strategies and privacy versus utility trade-offs to anonymize the local dataset in each clinical node. Then we actually developed a federated anonymization approach, which is applied across the clinical nodes network, the federated learning network that has been set up. And I will explain later why we actually developed this type of federated anonymization. And of course, synthetic data generation, which is one approach also for developing anonymized data, because synthetic data are anonymized data, and Imanol will explain better these new approaches for data anonymization. Now, in Synthema, we have heard throughout the prior webinars about the federated learning network, and today Sarah, of course, presented the data represented in RADDEEP, and Julie also the transformation to OMOP residing in the local clinical nodes, where the standalone anonymization engine also operates, and we have, of course, the Flower Edge Cloud nodes to then enable the federated learning, especially for training synthetic data generators. So, and we have, of course, a centralized aggregation server for the federated learning process. I will focus on the anonymization engine on its clinical node. So this anonymization engine is provided and resides close to the real world data. We said we cannot share real world data. We need to share anonymized data according to regulation. So the clinical data provider uploads the aggregated data set into the anonymization engine after defining the anonymization strategy in accordance to what the structure, variables, and semantics of the dataset are, and which methods are most appropriate for its direct or quasi identifier. The anonymization engine, based on the anonymization strategy, which also determines what would be finally the utility versus privacy losses indirectly, outputs the anonymized data, which can be stored locally, but then published also to the Synthema relevant catalog, the anonymized data catalog following the Health Decade AP metadata standard. And extracts, I forgot to mention, the anonymization engine extracts also the relevant privacy and utility metrics which accompany the metadata of the anonymized dataset when registered in the catalog. So this is the process actually. The important aspect is that we do define which are the direct and quasi identifiers in the dataset. And according to that, the appropriate anonymization algorithms, this is actually defining also the anonymization strategy for the specific dataset. And that, as I mentioned, leads to specific utility versus privacy trade-offs. And then we perform the anonymization and publish the anonymized dataset. Now, for the publishing part, why do we need to publish the description of the anonymized dataset in accordance to the Health Decade AP standard? The Health Decade AP, as a side note, is the one adopted also by the European Health Data Space implementations and efforts in the different projects that have been funded towards that target for cataloging shared datasets, clinical datasets. And it is actually the envisioned role and requirement from health data access bodies to use the standard in order to catalog the available clinical datasets. So why do we need this? As you may know, the DCAT AP, DCAT stands for the data cataloging. AP is application profile. The DCAT AP standard is the standard of choice for the European Open Data Portal, where any open governmental datasets are actually listed there, description-wise, not the real-world datasets. The Health DCAT AP is an extension to actually meet the requirements for the European health data space. It aims to support metadata interoperability within that data space and tries to uniformly describe, promote interoperability and enable seamless data exchange among researchers, public health institutions, policymakers, and other stakeholders. Again, it's an implementation approach for the secondary use of data in accordance to European health data space. And of course, a Health DCAT AP editor has been implemented in the context of the funded projects that all interested researchers and clinical providers can actually test and learn what the process will finally be. In Synthema, we have developed both approaches, anonymization that I explained, as well as anonymized dataset cataloging, which is used also for synthetic data cataloging that you see here. So indeed, on the local node, the clinical provider can ingest the dataset, start authoring the metadata for the Health Decade AP. Then the anonymization strategy needs to accompany the ingested data set, which defines, of course, what anonymization algorithms will be applied, and also determines indirectly the final utility retained and privacy achieved. Metrics when the anonymization process finishes The anonymized data, of course, is available, and I don't know if you can see very well, but also the metrics produced, the privacy and utility ones, are also listed as to the achieved values. And one can also see the description that according to the health ticket IP for this published anonymized dataset. Now in federated I don't know how, I hope you see, I don't know how this is hidden. In federated anonymization, we have, why have we introduced it? Because we have seen that effective anonymization cannot always be achieved when data comes from a single data owner. Why? Because they may be of low volume, as we have in Synthema with the rare hematological diseases. Data is scarce indeed in a single data provider, or it may be the case for infrequent situations that are met in other types of data. They may not be sufficiently representative, or they may have quality issues. So this impacts the anonymization performance because this then is performed in a suboptimal manner, and hence that increases the re-identification risk when these data are shared. This data set is shared. So the solution that we propose is federated anonymization that enables collaborative data anonymization at the desired quality and utility trade-offs across now the distributed nodes and data sources, not only on a single data source and data provider. And this guarantees that we have the desired volume and quality that we need in order to produce a high-quality anonymized dataset. So I will explain very briefly how this method works. Sorry for not adding more details, but this is still a publication in progress, waiting for feedback. So we do have in the federated network, as you know, the aggregation server, federated learning network, the aggregation server, the different clients, the clinical nodes, each one coming with their own data set. So what we try to do in federated anonymization is first to assess the quality of this dataset on its clinical node, and we have defined certain quality metrics. If the quality criteria are met, so the green shows the yellow first is that each client sends to the aggregation server the quality metrics, and the aggregation server, according to the quality criteria, decides which dataset will be used. Okay, with access, so in the green shows that it accepts that data to be involved in the anonymization process, or in the red means it rejects because it doesn't meet the minimum quality criteria. Now, once this is accepted, the datasets are accepted, local anonymization still is performed, but the dataset finally that is concluded is the one that fuses and aggregates all datasets from each clinical node. This federated anonymization has the low light that we need more time to anonymize, but in any case, in secondary use of data, there is no need to do real-time anonymization, since finally the data set will be set in a non-real-time mode. And it shows also that when we try to train a model using this anonymized data set, the performance of the training of the model and the accuracy is similar, both when we only apply local anonymization or when we apply federated anonymization. So this ends my part of the talk. I will now give the floor to Imanol to discuss about more advanced ways of anonymization, among others, using synthetic data generation. So Imanol, would you like to share your slides and me to stop?
Yes, I will share my slides. Thank you, Sofia, for the introduction. Okay, can you see my screen?
It's still coming. Oh, yeah, now yes.
Yes.
Okay. So, as Sofia said, my name is Imanol Isasa. I am a researcher in BeaconTech. I am also working together with Sofia and my colleagues in the Synthema project. and my main task is to generate synthetic data. So, of course, this will be a short presentation of what we are doing in Synthema. And after this, I will be happy to answer questions or contact offline so that you can have more insight on the project. So, first of all, I wanted to explain what problem we are trying to solve in Synthema. So here, as you can see in this slide, different institutions work like data silos. In this slide, you can see 4 different silos, and you can see that they are separated by walls. These walls represent a lot of things, right? Technical difficulties, a lot of bureaucracy, also regulations, and the actual scenario we tend to work in is the one that each data silo contains its own data, its own databases with their own aggregated or distributions or characteristics of the data. And it also may happen that the different data silos are located in different places in Europe or across the world, so must comply with different regulations. So all of this makes it difficult to collaborate in different settings, and different data silos tend to have their own artificial intelligence applications or models. So this limited access to data makes it harder for science and technology to progress or slows the process, especially in scenarios where the specific use case or disease in this context is scarce, for example, for rare diseases. So in this context, there is something that it is called synthetic data. So by definition, synthetic data is artificial data that was generated using an artificial intelligence model that makes it is similar to the artificial data. So the artificial data is generated from original data, so we need an input data set to reply or to imitate using these artificial intelligence models. So synthetic data is a solution to one of the previous problems I mentioned, which is the data scarcity, and it makes it possible for data silos to increase the amount of data they contain. So we would have, for example, in this slide, you can see that for each specific data silo, using a generative model to generate synthetic data, we could increase the amount of data we contain we have in this data silo. Of course, the synthetic data maintains the real distributions and characteristics to those of the real data we have used to train the models. But in this case, among the synthetic data, there is no one-to-one match with the original real samples. That is the main benefit, or one of the main benefits of the synthetic data. So in order to link it a little bit with the presentation that Sofia has showed us, in this slide you can see a comparison between what an anonymized dataset would look like in comparison to a synthetic dataset. Okay, so here in the left you can see a real dataset, an example of a real dataset that has specific characteristics. So in this case, an anonymized or a possible anonymized dataset would look like this, using the technologies that Sofia presented earlier. For example, this specific ID was tokenized, the age was grouped into different categories, and also the income. And for example, the BMI, assuming that this is a sensible feature, was deleted. And in contrast, a synthetic dataset would look exactly the same to the real one in terms of formatting and the number of features, etc. So comparing these two approaches, we would say that anonymized versions of the data tend to increase the privacy but lose in the utility of the information contained in the data, and the synthetic data aims to increase the privacy of the real dataset but also maintaining the utility. So synthetic data is used for different applications. One of them is data augmentation, which is the one I explained, and it is the one that we are using in Synthema. Also, it is used as a privacy-enhancing technology, and also synthetic data is used sometimes for testing purposes in order to test different demos or things like that. And there exist different ways or generative models to generate synthetic data. For example, in the context of Synthema, we are using GANs, generative adversarial networks. We are using autoencoders, diffusion models, and Bayesian networks. And of course, all of these models have their own limitations and, well, they have their own pros and cons. And the most appropriate kind of model should be selected depending on the application and the use case. But of course, synthetic data also has challenges or limitations, and the main one, or one of the main ones, would be this. So as I said before, in order to generate synthetic data, we need a reference, we need a real set of data. So the theoretical representativity or the diversity we can generate starting from that real set of data is limited. So we could generate up until a certain number of samples, and apart from that threshold, the quality of data would not improve anymore. So how could we solve that problem? Well, we could do it using federated learning. By definition, federated learning is a way of developing machine learning models where each federated device shares its local model parameters instead of sharing the data. So this means that, for example, in this slide, we have 4 data silos, as I explained before, and each contains its data set with its own characteristics and everything. But in this case, the artificial intelligence model or the generative model is trained in a federated way. That means that each data silo shares the model weights that they have obtained performing a small number of iterations or training steps on its premises, and then those weights are shared to a central server in order to build a bigger model that contains weights that come from different data silos. So that way, we could create a model that works with different data silos and that covers a wider variety of cases inside a same rare disease or different use case. I have to mention that there are 2 different federated, well, there are more, but 2 main federated learning settings, the horizontal one and the vertical one. In the left, you can see an horizontal setting where we are training central models with a same set of features in each data silo, but the patients in this case are different for each of them. And in contrast, on the left, we can see a vertical setting where we have same origins, we have same individuals from which we are getting the data, but each data silo is tasked to obtain or to train models with different features or different characteristics of those same patients. But of course, here we also have a trade-off, as Sofia mentioned, for the anonymized data. We have a trade-off between privacy and the fidelity and utility of the data. So as for our understanding, privacy is defined as the degree to which artificially generated data protects the sensitive information of real individuals. And the fidelity would be how accurately the synthetic data preserves the statistical properties, etc., of the real data we have used to generate that synthetic data. Of course, if we increase the privacy of the data, or we want to work with more secure data, we would lose the fidelity and also the utility or the usefulness of that data for downstream applications. And of course, if we want to maintain or we want to create a more useful data set, we know that the privacy protection would be less. So in this context of evaluating synthetic data, there are also a lot of different frameworks, a lot of settings, a lot of things to take into account. But the main conclusion we have to take from here is that the way in which we evaluate this generative synthetic data depends on the use case and depends on how or which metric we want to prioritize, for example, in this slide. So you can see here that we are separating the fidelity and the privacy components of the synthetic data evaluation. And in Synthema, we have two different use cases. The one in which we are working with acute myeloid leukemia and the sickle cell disease. So, for example, this is the framework we are using to evaluate the AML use case. So we are using the SAFE tool, which was developed by Humanitas, a partner in Synthema. And we are getting two different aggregated metrics, which are the clinical synthetic fidelity and genomic synthetic fidelity. Of course, each of these aggregated metrics contain a lot of metrics inside them, but there are a lot of things to take into account, but all of them are use case related, use case specific. And of course, there's a privacy section also, in which we are working with membership inference and attribute disclosure to evaluate the protection level we are giving to the generated synthetic data. Now, to explain a little bit the results we are getting from Synthema, here you can see the outcome of the SAFE tool I have mentioned right now. And for example, here in this slide, you can see three different models in different settings. So you can see that we have trained a CT-GAN, a Bayesian network, and a variational autoencoder. Each of them was trained for 4 different centers, which are the data silos in this regard. We have also performed a theoretical upper threshold by centralizing all of the data in a single dataset and training a CT-GAN model or one model with the complete set of data. And then we have performed a federated training of different models. So the tendencies show better performance in both the centralized and the federated versions of the models, of the different models. Both of them, the centralized and the federated, tend to improve the metrics obtained in different data silos individually. And between the centralized and the federated models, we can see that sometimes the federated version wins in a specific aggregated metric, and in some other cases, the centralized one wins. But we can conclude that both centralized and federated versions of the model improve the fidelity with respect to individual centers. Of course, we have to mention that the federated version of the models offer increased protection to the data because, as I mentioned before, the federated training processes are performed without sharing the data between different centers. This is the same use case for acute myeloid leukemia, but these are the results for the privacy evaluation we have performed, and of course the overall conclusions we can draw from here are quite similar. Both the centralized and the federated settings perform quite similarly, and we can see that Centers 3 is the one that gives more problems when taking into consideration the individual centers. This is due to the number of samples being used to train different models in the different data silos. And of course, we are using them, different metrics. We are analyzing, as I said before, different correlations, overall survival plots, etc., to evaluate the data. Now finishing, also as Sofia said, we are also working on a dataset catalog, but in this case, Sofia presented the anonymized dataset catalog, and we also are working on a synthetic version of that catalog. It will be an easy to access catalog, and a user would be able to explore synthetic versions of the data that were generated in federated scenarios. Now, to finish, I wanted to recall the opportunities and challenges that synthetic data in federated scenarios could bring to a project. As an opportunity, we could mention that we have stronger privacy preservation in federated scenarios and the synthetic data generation. The access to the data would be improved because federated learning would improve the collaboration between data silos. We would have improved AI robustness and better regulatory compliance. But we need to recall that there are some difficulties on performing this kind of trainings because the generative models sometimes are not that easy to train on federated scenarios. We have a lot of heterogeneity, both for talking about the data itself and computational resources. The evaluation of the data is really complex in federated scenarios, and this is something that we are also working on in Synthema. And the communicative and computational cost in each data silo in a federated network also is something that it is really challenging. So this was all from my side. As I mentioned before, I am happy to answer different questions, or if you want to connect offline, there is also my email in the first slide, so that you can drop me an email, and I will be happy to connect with you. Thank you.
So I see a question in the chat. It says, apologize if it was already discussed. How do you handle federated learning when datasets coming from different clinical providers have different features or variables stored in different data types?
Yeah, that is something that I was mentioning in the last slide. It is related to the heterogeneity of the data, well, both the data and the computational resources of different data silos. So when clinical providers have different features, that would be more on the vertical federated learning side, and that is something that we are not covering in Synthema. But we are dealing with differences between how the data is being collected in different data silos. And that is something that we are managing by defining like a common data model, so that all the data silos could stick to that data model, and then we will not have any problem in training federated models. But of course, it is something that it is difficult and requires a lot of communication between data silos. Yeah.
Okay, we don't have any more questions, so we can jump into the third and last block of speech of this session. So, Rafael, I don't know if you want to share your screen.
Okay, I'm doing it.
The order is supposed to be Rafael, then Ines, then Max, and finally Jan, just for you to know.
Okay, so here is it. I assume that you can see the slides and you can hear me well. Otherwise, let me know.
Yes,
So my
we
name
can
is
see
Rafael.
you.
Okay, my name is Rafael Redondo, director of the Multimedia Technologies Unit at EuroCAT, and I'm going to talk about the medical image synthesis, probably in a more academic point of view today. And this is part of the work that we've done in the Phase 4 AI project that aims to build a federated health data space to improve diagnosis, where data synthesis, we've seen in the previous presentation, is a fundamental pillar due to the overall data scarcity that we have and the regulatory barriers in the health sector. So among the two use cases we have in the project, I'll focus in this presentation on lung cancer, the deadliest cancer in which early detection substantially improves chances of survival. Have we seen the utility of the medical image synthesis? There are different uses that we can have from that. And in our context, we've seen that synthetic data can contribute to shared data with privacy guarantees, but it can also contribute to downstream tasks, such as to alleviate the data scarcity, to improve disease detection or segmentation models, but also reducing scan times, for instance. And recently, genetic models have been used as predictors of disease evolution when conditioning on longitudinal data. This is a quite recent usage of the synthetic data. Very interesting. And so what are the current genetic models capable of? They are able to learn complex distributions implicitly. That means that there's no need for complex explicit modeling, which is costly and very difficult. And as a result, we can synthesize complex data distributions such as volumetric CT or MRIs with high fidelity and generate not copies, but new samples. To improve reliability, these models can be optimized on conditions of each clinical context. They also allow access to prediction probability, and they are visually interpretable in the case of images. However, they could still generate plausible artifacts, what we call hallucinations, and which are difficult to quantify and mitigate. Nowadays, the state of the art of image generative models are diffusion models, and this is an example, part of publications we recently had. Diffusion models are a particular type of deep neural network that is able to iteratively reverse noisy diffusion process and approximate at the same time the probability distribution of the training data. In this case, the black volumes that we have on the left-hand side. Once trained, the diffusion model can draw new samples from on demand. That's an important feature, and from purely random seeds. And a useful trick we have here is that we can guide the denoising process by conditioning the model with anatomical mask of the lens or the nodules. This is an example of a purely 3D synthetic 3D CT scan in high resolution. And also we can guide the model, as I said, with anatomical mask of the lens and in magenta and the nodules in cyan. So the model respect those morphologies, as you can see in the bottom line. Also, we can condition the model with the textures of the nodules, so we are able to generate the same nodule with across different values of solidity. 3D And so how would you measure the quality of synthetic data, which is not trivial? Let's group here the image quality metrics in three main groups, some of them already addressed in the previous presentations. First, we have the objective metrics that use statistics to measure how close two data distributions are, what we call fidelity. And typically we have in images the fetched inception distance, and recently the fetched radiomic distance for images. To measure variety, we use pairwise image similarity metrics. And to measure authenticity, we could use the ratio between reals versus copies in a batch based on similarity metrics. The main limitation of these metrics are these metrics are data biased. They are not tailored to medical domain or clinical applications, and they depend on this threshold that in order to measure whether we have a new sample or a copy. In the second group, to assess the objective utility of synthetic data, when we use to augment the synthetic data, the real data sets, we find specific metrics for each use case. In the lung cancer imaging, there are specific metrics to measure the accuracy of the nodule detection, also the localization, and also the morphology. And complementary, we could measure the performance of the machine learning methods just on the synthetic data. So the idea is that they should perform equally on real data compared to synthetic data. These metrics are specific for clinical applications, which is good, but they are biased to the model that we use to measure the quality of or the performance of this synthetic data, and so that they have low interpretability. In the third group, we have the subjective metrics. In which the synthetic data is evaluated by experts and the subjective score opinions, which can be tailored specifically for clinical purposes, different ones. However, is highly time-consuming. As part of the study, these are results of our methods compared to other methods of the state of the art across fidelity metrics and similarity metrics that measure the variability of the synthetic data sets. And in the bottom line, you see a comparison of textual descriptors, three different textual descriptors between real and synthetic data sets, and the idea is that they should look alike, which is the case. So let's move on to the utility assessment of the synthetic data. In our case, what we did is to train machine learning, a deep neural network to segment the nodules, train on a real data set called LIDC, and with and without augmenting with our synthetic data set, what we call ANT. And what we found is that we improved the segmentation results. On the right hand side, you can see the ground truth. On the left hand side, you see the segmentation without the synthetic data. And in the middle, you see the results by augmenting the real data set with the synthetic data set. So we can reduce some artifacts here and more accurate segmentation mask. And this is another example with similar results. And also we see it visually, but we can measure it and quantify in this case by using this DICE metric, which is the intersection of a unit of the segments. And we see that the results improve. So conclusions is that generative models synthesize images with high fidelity, the current state of the art, although there is clinical relevant inconsistencies to mitigate. Image quality metrics are not fully aligned with clinical aspects. And also synthetic data could balance real data sets, although its clinical validity is critical. Another one is that privacy metrics often rely on subjective or arbitrary thresholds that we have manually adjusted. And in my opinion, the most important challenge is how to bridge the technical advances that we see with the regulatory frameworks. So how to translate these metrics, mathematical metrics, such as fidelity, variability, or privacy, into measurable, auditable criteria. And this is all from my side. So if you have any questions, I'll be glad to answer them on the chat. Thank you.
So next one would be Ines. I don't know if you want to share your screen.
Yes, sure. Just 1 second. Okay. Can you see my screen? Please confirm.
Yes, we can see it.
Okay, thank you. Good morning, everyone. Thank you for the invitation. I will be speaking a little bit about the AI SimFormat project. It's a project funded under the same call as Synthema, and we also have similar objectives, which I will make clear. So, of course, this is common to all projects that we want to develop and enable technological tools that are able to maintain healthcare data secure and at the same time be able to leverage this data for machine learning purposes and artificial intelligence, create artificial intelligence tools. So, of course, the healthcare data is sensitive and should remain private, but is also sometimes unbalanced and incomplete and unstructured, and is biased because when we certain hospitals have a regional bias. Sometimes we also have that in some hospitals we are more specialized in some kind of patients or diseases, and even when we consider hospital data, this is biased towards disease and many times lacking the healthy subjects. But to increase the efficiency of healthcare, we really need to unlock this potential of health data because it allows us to create solutions that are may turn the healthcare systems more efficient and also increase the knowledge we have about certain conditions or treatment options. So the consortium, AI SimFormat Consortium, is this one, different partners across Europe with different backgrounds and knowledge. And we have our approach to this issue has been to create a platform in which we connect data providers with machine learning engineers and data scientists. And so the data providers are able to upload their data, and they have some tools that enable them to make a easier data governance, to govern the access to data and be sure that their data is held secure. And this is done through federated data hubs or through a cross-borders health database. In the case data is anonymized, or we have informed consents that enable the use of this data. The data scientists and ML engineers are able to access the data and train their models, to validate models they may have already with different data sets from different centers, also to generate synthetic data, evaluate the data and the models. For the medical experts, they are able to explore data from different sites and also to explore the models that have been created and are available in the platform to classify or to predict certain characteristics of disease. So today I will speak more, so this is overall the general view of the project. I will speak in more detail about a specific use case for synthetic data generation we have been working in this project, and is related to chronic heart and respiratory diseases monitoring. And this specific use case is based on a data set that has been collected for research purposes. So it's a very small data set because it's this kind of data collection requires experts to be involved in the data processing, in the data collection and processing. So contacting the patients, performing different questionnaires, different tests, different visits in time. Is a very complete data set, but with very few patients. We have only 254 training samples. But this happens in real world, this happens in practice, and we thought that maybe synthetic data could help us extract a bigger value and extract more knowledge about this data set. So what we did was, so we have 24 clinical observations in 3 time points, and we have sensor measurements, patient reports, clinical reports. So just to explain a little bit, these were patients with heart failure or chronic obstructive pulmonary disease that have been admitted to emergency. In the first episode of emergency admission, a group of experts performed these questionnaires, these clinical reports, and also with some sensors to measure heart rate and O2 saturation. They performed a walking test in the hospital, and they collecting this sensor data. Then, after some time, they called the patient, they verified the patient has stabilized again, and they repeated this intervention. And at third time, the same questionnaires and the tests were repeated. So the data collection is a laborious process, involves specialized personnel, and the dataset size is limited, which presents a risk for overfitting. Of course, we can train a machine learning model with this data, but the risk that the model is very overfitted to the data that has been collected is very high. So we were trying to understand if with generation of synthetic data we could improve the reliability of the model. So we proposed a specific approach for synthetic data generation. This is a variational autoencoder that has been modified. In particular, we introduced an input masking to make sure that the generative model would learn the most diversity of the data set. So we hide parts of the data set to force the model to learn all the different patterns that may be present in this small data set. And then we did a very consistent evaluation, which we have several use cases in the project, and we have proposed this methodology for evaluating synthetic data, which is transversal to the different use cases. So first, we do a quantitative evaluation. We compute different metrics for fidelity, diversity, and privacy. So these are the pillars, but then we have specific methods within each pillar that may be more appropriate depending on the data modality, on the use case. And we compiled all of these in an open source library. This PyMDMA library is open source, you can use it. So what we did was we compiled all the metrics available in the literature for data quality evaluation and specifically for synthetic data evaluation under these pillars: fidelity, diversity, and privacy. Then for machine learning utility, we trained a classifier, a machine learning model, and we trained this model just in the real training set, and we held out a test set of real data. That is, so the evaluation of this classification predictive model is always done in the real held out data set, and the model is trained either only on the real training set or in a combination of real and synthetic data for the training set. So this is how we evaluate utility for the machine learning task. And then we also have a process of human evaluation that I will explain that later. But for now, so these are the results. This is the method we proposed, the TTVIE-MMD. So evaluated with the metrics of data quality under fidelity, diversity, and privacy. And we have here for the machine learning utility, the baseline, which is train in real data and test in the held out real data. And we have in the yellow dot the performance of the machine learning model trained with real and synthetic data. And we compared with other more standard state-of-the-art approaches like GAN or the traditional approaches of SMOTE, or these are traditional augmentation methods or random sampling. And we see that, in fact, comparing with the SMOTE, for example, which is widely used, SMOTE just repeats some data samples. And we see that, fidelity is really high because actually we are copying data, but privacy is 0. And the gain in machine learning utility is very, very low. For random sampling, what happens is we sample new data points from the statistical distributions of the data, but per feature. So there's not really realistic coherence between the values. And we see that in this case, fidelity is very low, but privacy is very high, of course, because this is new random samples. And we see that it helps a little bit to improving utility. But the biggest gains were actually with the synthetic model that was tailored for this purpose, the variational autoencoder. So for the Doctor in the Loop human expert evaluation of synthetic data, we thought, okay, we have a comprehensive evaluation of synthetic data. We look into specific quantitative metrics of the data. We evaluate the utility in downstream machine learning tasks. But there are still some points related to the clinical plausibility of the data that are not fully covered under this pillar. So it can happen, for example, and this is another use case, we have images of the retina. Imagine you can have some lesions in the retina, but they are never anatomically, biologically, they can never be on top of a major blood vessel. So it doesn't not happen in nature. This specific type of lesion is not appearing on top of a blood vessel. But for the synthetic generative model, actually this can happen. So, and none of the metrics we compute will be so fine-grained to uncover these patterns. So we thought, okay, maybe we should have also a clinical evaluation and try to understand which are these patterns that the metrics are not being able to cover. So we did some co-creation workshops. We talked with very different clinical research groups and the different specialties and modalities. So we have different sessions with paper mock-ups to understand this is a new task for clinicians. How should they evaluate synthetic data? And we know that they can be easily tricked when we show two images, but this is a little bit, we thought that how can we make this more to the point, more optimized, and make the most value of the limited time of our experts. So we tried to have some categories and for them to try to uncover these patterns that may happen in synthetic data and are not plausible. Yeah, and so we have done this process with the use case I showed you. So this is the interface they have. They have an explanation of the purpose of generation. We show a little bit what is the real data used, the generative model used. And then, so we have here in the, I don't show these tabs, but here they can see the real data set information. They can see even statistics about the features. They can see the statistical variance, the maximum, minimum values. They cannot see specific real data points, but they can have a very good overall understanding of the real data set. And then we show the synthetic data set, sample by sample, and they can mark each sample, or they can choose a set of samples and filter values and then register if this data point is realistic or not. and choose some reasons for the most common reasons for this unrealism, and also add, of course, additional information if they want to. So we have been evaluating this for this use case for the tabular data. We are still in the process of iterating and improving this approach. And what we see is, of course, some preliminary conclusions I can share. For synthetic health data evaluation, one of the main points is the scalability, because of course doctors are not able to see, we can generate infinite amounts of data ultimately, and they are not humanly possible to review all of them. So one of our research questions is how to choose, how to prioritize the cases that can we use the metrics, we use some quantitative information to guide to the cases that need human revision. And then the agreement rates between the doctors. So we are still evaluating if under this framework and with the options that may be selected, if the agreement rates are good or not. And so far they have not been so good. So we feel that we still have work to do. Yeah, that's all from my side.
Thank you, Ines. So we move to Max now.
Okay. Hello, everyone. Nice to be here. My name is Max Salmi. I come from the FEMS EU project and company, technical partner in FEMS, a company called Veil.ai. So why this FEMS project got initiated in overall in the beginning? Well, basically, the whole project is built around pediatric hospitals, and the reasons are obvious. Also, when we think about the previous presentations, so in a single pediatric hospitals, of course, they treat rather small number of cases, and typically, let's say in a European country, you might have only one, maybe two children hospitals. So these children hospitals are really scattered around the Europe, and the data from one hospital is not really sufficient for research. But nonetheless, the hospitals need to and want to perform better to treat the children, and also acknowledge that they need technology partners in order to do this. So a very, I think, practical reasons why this consortium and project got initiated. Sorry. So this is sort of the background why FEM started, and what are the objectives? So there are basically three high-level objectives. They want to, of course, accelerate the research, especially in the rare disease cases in pediatric world, and of course improve their how they treat the patients and the quality of it. We all know that the healthcare sector is a very tough one. The resources are limited, and so you have to do every day. You have to do a bit smarter in order to stay there. And of course, it's all about the patients in the end. So then we want that the children and kids who come to these pediatric hospitals, that they will actually then be treated in better manner and more efficiently and with better outcomes. And now you also here see the PHDS, which is sort of how FEMS wants to continue. So comes from the pediatric health data space, sort of following the EHDS concept. So after the project, these hospitals will want to continue to form a network where these objectives can be achieved. And let me then go to very similar topics that the others already have presented. So everybody are rather familiar with the terms here. So there are 3 topics in FEMS that we want to tackle. There is this data standardization, which is of course necessary in order to operate any federated network, which is then the sort of interoperability layer in FEMS. And then we have, of course, the question of data privacy, since especially with children, it's we want to be extra careful in terms of the privacy. So from the data standardization point of view, all of the hospitals have their data in OMOP CDM, and this is, of course, the ground to actually have a operational federated network functioning between these hospitals. So we have 4 hospitals who are connected in this federated network, where basically the federated work is divided into 2 separate concepts. So we have federated analysis, which is sort of maybe a bit more simple one, where you send a query, which is then distributed over the network, and you get the results back, and you can then combine and receive the information from the network. So this is sort of a single pass analysis. And then the more complex one is federated learning, where of course you distribute the model training over the network, but there you typically do multiple queries to the data during the training. So this is of course from IT and operational perspective very complex, and how do you build this and maintain these kinds of infrastructures operationally. And as we know, federated network or federated architecture is a privacy enhancing technique, but we wanted to complement that also with data anonymization and synthetic data generation capabilities. So for example, with the federated learning, we actually are evaluating that what if the model training is actually done with the anonymized synthetic data rather than the real data, because from the governance and legal perspective, it is really difficult for data controllers to allow any processing on the sensitive data. So there are, when we come in the real world and the practical operations, there are of course these brick walls that were also mentioned in one of the previous presentations. So I think it's great that we all work on the same topics and in different fields and see how we can get these into action so that we can improve things here in Europe. The hospitals here are coming from Finland, then so HUS, Helsinki University Hospital, then we have Rotterdam, Erasmus, then we have Saint Jean de Dieu from Barcelona, and Great Ormond Street Hospital from UK that are part of this federated network in FEMS. Then a bit, because we are focused on the data anonymization and synthetic data generation, so this is also an essential technological component of the PHDS. So we want to bring additional safeguards before these federated analysis or learning processes. And that's something that we are evaluating and testing in FEMS project. Also, quite often researchers and others who want to use the data of these hospitals, it's typically rather long process to actually understand what there is. So this is also something that we want to accelerate the data access, that people could understand what data is available in which quantities and what type of data there really is. Can I validate sort of quick feasibilities that can I do my research on this data, or do I need to go somewhere else? And of course, before any data leaves or access is given, the data controllers want to ensure that the data is anonymous and there's no sort of illegal mistakes made from this perspective. Like I think mentioned also in the previous presentations, also here the application that is doing the data anonymization and synthesization is deployed very close to the sensitive data, and it's not part of the federated architecture as such, which I think is a good choice. And I think, well, there are multiple techniques. We have the generative models, we have other methods and techniques. So it's interesting to discuss in the field also about the terminology when people use the term anonymization or synthesization, what people think about it. So for us, it's important that the data is in the end anonymous, no matter what has been the technique to create it or produce it. Yeah, we are a small company from Finland, from Helsinki. If you want to connect with us, you can see our web page there or take the QR code. But yeah, I think this is shortly about the FEMS. The project is coming to its end this year, and indeed wants to continue then after the project phase as a operational pediatric health data space where pediatric hospitals can join the network and improve their health and do benchmarking with other hospitals and improve their delivery of health. So it's very, very interesting and nice to be as a technical partner in this kind of setting where good things are done for the young people. Okay, that would conclude my short presentation about FEMS and its sort of data operability topics. Thank you. Any questions are welcome, of course.
Thank you, Max. So I don't see any questions in the chat. I think it was then all very clear for all the presenters. So then I think it's okay to close the session for today, and we welcome all of the interested.
No, Alva, sorry. We have,
Sorry, Sarah.
Yeah, no.
Yeah, true. Sorry.
It's okay. This is the last one, Jan.
Hey, good. So give me a second to share my screen. I hope you correctly see my screen. Yes. Good. So I will just offer a few comments on synthetic data generation from the perspective of the FLUT project. My name is Jan Ramon. I work in INRIA, which is a computer science research institute in France. No. Oh, there is a problem. I'm sorry. Happens. Yeah. Okay. Good. So the FLUT project originates from the consideration that we need to learn from cross-border data. Often data available in one single hospital is not sufficient, for example, because modern AI models require lots of data, so more than you have in a single hospital. Others, on the other hand, also because learning from a single data owner, a single location, doesn't give you sufficient geographical robustness to apply your model also at other locations. This immediately brings a number of challenges. For example, if you collect data from multiple locations, then there are concerns about data protection. So therefore, the FLOOD project developed a privacy-preserving federated learning approach, which is regulatory compliant and which does not require the data to leave the several data owners. So data owners keep their data, they exchange encrypted messages, so that in the end, the statistical model you try to infer can be extracted without anybody ever seeing the data. On the other hand, there is a need for standardization because the data of the several hospitals is entered by different people, different instruments to measure the data. The different locations may use different standards, units, software systems, national regulations, etc. So there is quite some diversity in Europe, which is often good, but standardization is needed to be able to combine all data together and to extract better AI models out of them, which also applies for synthetic data. The FLOOD project considered a use case in prostate cancer. So typically when a patient has symptoms, the first thing one does is to do a blood test. Then if it turns out that the PSA level is too high, one goes further, one makes an MRI image. And then the next step is to decide whether a biopsy is needed. A biopsy typically is a procedure which is painful for the patient and costly for the society. So we don't want to do that necessarily, while on the other hand, we don't want also to miss clinically significant prostate cancers. So the question we try to solve in the FLOOD project is, given a number of clinical variables and an MRI image of the prostate, can we now predict whether a biopsy is needed or not? Good. In the project, next to other predictive modeling, we also considered synthetic data. Why do we need to look at synthetic data in the context of this project? Well, there are essentially two reasons. On the one hand, you could use synthetic data to train humans in the case you can't show the humans the sensitive real-world data. On the other hand, synthetic data can be used for data augmentation, where we add synthetic data to the training set in the hope that the training set, by getting larger, will allow to improve the training of our predictive models. We considered several types of synthetic data. Synthetic data of tabular data, of image data, and then combined multimodal data. There are many different models to generate synthetic data. On the one hand, for tabular data, we, after a comparison, selected algorithms in the style of the OMOP algorithm. The idea there mainly is that one repeatedly removes a feature from a particular instance and replaces it by probabilistically generated features which you compute from the still remaining feature. This is in a centralized approach, quite interesting algorithm. It turned out to be quite challenging to make of this privacy-preserving federated learning algorithm due to the fact that this UMOP approach is quite instance-based. So at a certain step in this algorithm, one needs to apply the k-nearest neighbors algorithm, which requires to compute distances between instances which are private, so you don't see them. You can, of course, encrypt the complete calculation of the distance, but that's quite expensive. So this is not an easy algorithm to lift to the federated level. On the other hand, we also considered data generation strategies based on GANs, autoencoders, and diffusion models. As these are neural network based, these can follow the classical federated learning approach, where one does secure aggregation of gradients and then stepwise updates the model to better be able to regenerate the data. A disadvantage of this type of models, which are especially intended for image data, is that huge amounts of training data are needed. And this is often a challenge in, let's say, healthcare, that the amount of data is limited, even if one goes to the union of multiple data owners. So there we obtain a number of results. However, we expect that higher quality image generation is possible by still learning on larger amounts of instances. Okay, so we validated the synthetic data generators in several ways. On one hand, we validated synthetic data based on distribution, which means that mainly you try to check whether the distribution of your synthetic data is close to distribution of real data. For example, you can isolate individual properties, and then it is reasonably easy to check that the distribution of the two real and synthetic data sets are close together. This is only an approximate evaluation strategy, of course. More qualitative approach is to let the synthetic data be validated by human experts. So we asked radiologists to look at the synthetic data. Unfortunately, the disadvantage is, of course, that these human experts are more expensive. They don't have that much time, but good. So they can better evaluate whether not only the individual parts of an image makes sense, but also whether the image makes sense as a whole. We also can use data augmentation to evaluate synthetic data generation. So one would hope that synthetic data improves supervised learning results if one adds it to the data set, and in this way make data sets larger. This is also what we see for the tabular data. As I said, for the image data, the synthetic image data generation is quite challenging, partly because the number of instances, the number of images is limited. On the other hand, also because these images are three-dimensional, which is more challenging than the more classic two-dimensional image synthetic data generation. There we observed that, okay, good, the improvement in supervised learning is limited and not as good as what alternative strategies, for example, foundational models, which I will discuss later on, offer. As said, an important challenge is to guarantee privacy. We can guarantee the privacy of the data during the training process. It is also, of course, important to ensure that the synthetic data generators are private and that the generated synthetic data is private. Synthetic data is not necessarily private if no dedicated effort is done. It can contain pieces of the original training data. So therefore, many approaches over the last years have considered to use differential privacy to have a better guarantee that the generated synthetic data, both the generators and the data itself, satisfy certain privacy guarantees. Okay, as said, the quality, the utility of synthetic data towards data augmentation and improvement of the training process is well, exists, but is not perfect. So in the Fluid project, we also considered the alternative of using foundational models. Foundational models are based on self-supervised training, where, for example, one tries to predict a pixel given the rest of the image. This idea is a bit similar to the OMOP synthetic data generation strategy, where also you try to predict a feature given the rest. The advantage is that you can capture in your foundational model patterns you see in training data, that not all your training data needs to be complete, nor it needs to be labeled. You can also learn foundational models from unlabeled data or partial data or data which has other resolutions, etc. And this gives some advantages, especially if we can learn from, for example, in several stages. First, we learn from arbitrary images, then we learn from medical images, then we go to prostate images and iteratively train the model in a more specialized task. Then at a point where we come to training the model to determine whether there is a clinically significant prostate cancer lesion in the image, at that point, training goes much faster. And the number of training examples needed to learn the final task is reasonably limited. So there our conclusion would be that foundation models are a related model which don't exactly generate synthetic data, but use similar approaches, but help more in terms of speeding up supervised learning. The disadvantage is, of course, that you don't generate images themselves which you can, as a human, contemplate, and so the model itself may remain a bit less interpretable. So in conclusion, synthetic data can help to get a feeling of how the data looks like. So this is useful for training and for exploring the data. and it can help to improve performance of supervised training. Even though that, okay, as said, the foundational model alternative is something to be considered there. There are a number of challenges, such as the fact that synthetic data generation is not very easy to evaluate. There are a number of indirect evaluation strategies, and the amount of training data, at least in our specific use case, we need is quite large. Okay, thank you for your attention. If you have any questions, I'll be happy to answer.
Thank you, Jan. So I think that people have been making exchanges in the chat, but there is no specific questions. So now, yes, this is the end of the session. I want to thank you all for your participation and for your presentations. And now, wishing you all a very nice weekend.
Thank you. Have a nice
Thank you.
afternoon.
Thank you.